I want you to try something for me right now, wherever you are, maybe driving, at the gym, whatever. Just focus on the sensation of your feet on the floor.
Uh-huh.
Can you feel it? A few seconds ago, you weren't thinking about your feet at all. The data was there, but you weren't, attending to it.
Right. It was just background noise.
Exactly. And now, suddenly, you, this conscious self, just directed a spotlight onto a physical sensation. It feels incredibly simple, doesn't it?
It feels like the most natural thing in the world. It's the baseline of our existence.
But that's the whole problem, the thing that keeps scientists up at night. That feeling of being you. It's generated by, well, a lump of biological matter.
3 pounds of wet, salty meat inside a dark skull.
How on earth does a firing neuron, which is basically just a biological switch, a spark turn into the taste of coffee, or a memory, or that feeling of your feet on the floor?
That is the hard problem of consciousness right there. How do you get subjective experience, the feeling of what it is like, out of objective physical stuff?
Usually when we talk about this, things get very philosophical very fast.
We start talking about souls and spirits.
Right. But today, we're doing something different. We are taking a deep dive into a fascinating report called Consciousness Emergence, Microdynamics to Macro States.
And what's great about this source is that it doesn't just throw its hands up and say it's magic. It treats consciousness like an engineering problem.
It's a technical blueprint, almost. It's trying to bridge that gap between the hard stuff, neurobiology, complexity science, and the soft stuff, which is your actual experience of being alive.
By looking at the brain as a kind of hierarchy.
So our mission today is to climb that ladder. We're going to start at the very bottom with the microscopic war happening in your synapses right now.
And then move up to why your brain needs to sit on the edge of chaos to think it all.
And finally, we'll get to this mind-bending theory that you, the thing listening right now, are basically a user interface your brain built for itself.
It's a heck of a journey. And along the way, we're going to explain why sleep isn't just rest. It's a destructive process you absolutely have to pay for learning.
I love that. The price of plasticity. Okay, let's do it. Let's start at the foundation, the microdynamics. The report calls this the war at the synapse. That sounds dramatic.
It really is a conflict, a constant push and pull. You see, to understand how the brain works, you have to realize the system is torn between two opposing forces.
Okay, what are they?
On one hand, your brain is desperate to learn. It wants to connect things. On the other hand, it has to stay stable so it doesn't just, melt down.
So that gets us to that classic phrase, neurons that fire together, wire together.
Right. That's Hebbian plasticity. It's the basis of all associative learning. If you smell a rose and see the color red at the same time,
The neurons for rose smell and red color fire together.
yeah, the physical connection between them gets stronger. So next time you smell a rose, you're more likely to think of red.
Simple enough.
Yeah, and the report gets into the weeds on things like long-term potentiation, or LTP, but it also brings up something called BTSP.
BTSP, behavioral timescale synaptic plasticity. It sounds complicated.
It's a bit of a superpower, actually. Traditional learning models need tons of repetition. But BTSP helps explain one-shot learning.
Like when you touch a hot stove once and never do it again.
Exactly. It uses these bursts of calcium inside the neuron to signal, hey, this event is really important, lock it in right now.
Okay, so these mechanisms, LTP and BTSP, are strengthening connections. We're learning. That sounds great. Where's the war?
The problem is that Hebbian plasticity is a positive feedback loop. Think about it. If the connection gets stronger, the neurons are more likely to fire together next time, which makes the connection even stronger.
And on, it would just spiral.
It would spiral into runaway excitation. Basically, the brain would scream itself into a seizure.
Or the other way, I guess. It could just go silent.
Precisely. A system that only cares about learning is inherently unstable. It will always crash.
So nature needed a stabilizer, a peacekeeper. This is what the report calls synaptic scaling. And I love the analogy they used for this.
The stereo analogy.
Yeah, walk us through that, because it just clicked for me.
Okay, so imagine a memory is a song. The song has drums, bass, vocals. The actual information, the memory, isn't the total volume. It's the mix. It's the ratio between the drums and the vocals.
Right. That relative difference is the data.
So, as you learn during the day, Hebbian plasticity is cranking everything up. The drums get louder, the vocals get louder. Eventually, the speakers start to distort.
It's just too loud. You lose the clarity.
Exactly. Synaptic scaling is the brain's way of reaching over and turning down the master volume knob. It lowers the strength of all the synapses.
And this is the key bit. It preserves the ratio. It keeps the mix the same.
It keeps the mix intact. The drums are still louder than the bass, but the whole system is back in a safe, non-distorted range.
And it does this by physically removing receptors from the synapse. Like, it's actually dismantling the hardware.
Yes, it physically scales down the sensitivity. It pulls out those AMPA receptors.
Which leads to maybe the most practical insight in this whole deep dive, the synaptic homeostasis hypothesis, or SHY.
It totally reframes sleep. We think of it as just resting, but SHY says it's an active metabolic necessity.
It's the price of plasticity.
It is. Every time you learn, you build stronger synapses. That costs energy. It takes up physical space. You literally cannot do that forever. You'd run out of fuel and saturate the system.
So sleep is the cleaning crew coming in.
It's an active downscaling process. When you're in deep, slow-wave sleep, the brain systematically weakens those synapses back to a baseline. It saves energy and frees up room for the next day's learning.
So if I pull an all-nighter to study for a test,
You're trying to write data onto a hard drive that's already full. And not just full, but noisy and energy depleted.
Yeah.
You haven't paid the bill for yesterday's learning.
that's a powerful argument for getting your 8 hours. It's not lazy, it's system maintenance.
It's essential.
Okay, so that's the basement level. We have this constant cycle of wiring up and scaling down. Now, let's climb the ladder to level 2, the shift from reflexes to prediction.
Right. This is where we go from the causal brain to the computational brain. Level 1 is just your brainstem, basically.
Heartbeat, breathing, basic reflexes, input equals output, like a thermostat.
Exactly. And a thermostat isn't thinking. But at level 2, the brain starts doing something revolutionary. It becomes an error-minimizing prediction machine.
It stops just reacting and starts guessing what's going to happen next.
Yeah, and the source calls this epigenesis, which here means a kind of neuronal Darwinism. The brain throws out a bunch of predictions, and the ones that match reality get reinforced.
The ones that fail get pruned away.
It's constantly tuning itself to the environment.
And the thing that tells the brain, good job or bad job, is dopamine.
Dopamine is critical here for something called credit assignment. This is a really tough engineering problem. Say you swing a golf club, and 3 seconds later the ball drops in the hole. That's a reward. But how does your brain know which muscle twitch from 3 seconds ago was the right one?
Because you did a million other things. You blinked, you shifted your weight.
Right. If the brain just rewarded everything, you'd learn nothing. Dopamine acts like a time-traveling tag. It bridges that gap and says, hey, that specific action led to this reward.
So it solves the credit assignment problem. But here's the catch, and the report quotes Joshua Bach on this.
Yes.
At this level, the system is super smart. It predicts, it learns, but there is no self.
Correct. It's a zombie engine, a philosophical zombie. It can process complex information and produce complex behavior, but there's nobody home. It hasn't built a model of itself yet.
So how do we get from a smart zombie to a conscious being? This takes us to level 3, and the report points to 2 big ideas, ignition and criticality.
Let's start with ignition. This comes from the global neuronal workspace theory. The idea is your brain has all these local unconscious processors, vision, hearing, motor control,
All doing their own thing in the background.
but occasionally a signal is strong enough or important enough that it ignites.
It breaks out.
It's a non-linear explosion. Once it hits a certain threshold, it gets broadcast globally across the entire network. Suddenly, that piece of information is available to your memory, your language centers, your planning centers.
And that global availability is what we call conscious access.
That's the theory. Yes. And the system is exclusive. You can only have one thing ignite at a time.
Which is why we have a single stream of consciousness, not a total chaotic mess.
Exactly. And that's thanks to something called inhibitory surround. For a spotlight to work on a stage, the rest of the stage has to be dark, right? Special GABAergic neurons create that darkness, suppressing all the competing signals so one thought can dominate.
Speaking of chaos versus order, this leads to my favorite part of the report, the critical brain hypothesis. The idea that the brain sits on the edge of chaos.
It sounds unstable, but it's the sweet spot. This is a huge idea from complexity science. It suggests the brain tunes itself to a phase transition point, self-organized criticality.
So it's right on the border between being perfectly orderly and completely chaotic.
It has to be. Think about it. If your brain was too orderly, it would be like a crystal. It's static, frozen. No information can flow. You'd be in a coma.
And if it's too chaotic?
It's like a gas. Random noise. Information just disintegrates. So the brain finds this sweet spot, this edge.
And what happens at the edge?
You get what are called neuronal avalanches.
Yeah.
A small input can trigger a cascade of activity that travels across the whole network. Doesn't die out, but it doesn't explode into noise either. It's the perfect state for transmitting information.
And this is measurable, right? It's not just a metaphor.
Oh, yeah. We can see the signatures of criticality in brainwaves when you're awake. When you fall into deep sleep or go under anesthesia, those signatures vanish. The brain leaves the edge of chaos and consciousness fades.
That's an incredible image. We're surfing a wave that's always about to crash.
It is a dynamic balancing act, absolutely.
Okay, we've ignited the workspace. We're on the edge of chaos. Now we're at the summit. Level 3, the psyche.
Right. This is the big shift. The system stops just modeling the world and starts modeling the agent inside that world. It's self-organizing meta-learning.
And the report brings in Integrated World Modeling Theory, or IWMT. Can you give us the simple version?
The core idea is actually pretty elegant. IWMT says that consciousness is what integrated world modeling feels like from the inside.
So it's the feeling of being the thing that's doing the modeling.
Exactly. The system starts asking who is doing the predicting. To do that, the report says the brain uses something called SOHM, self-organizing harmonic modes.
That sounds like serious technobabble. Harmonic modes.
It just means resonance. Think of a guitar string.
Mhm.
It has natural frequencies it likes to vibrate at. The brain's network has those too. SOHMs are just large groups of neurons all resonating together, humming in the same key.
And that lets them share information instantly.
Right. And this resonance allows for something the report calls turbo coding.
Now we're getting into fast and furious territory.
It's a real term from communications engineering. It's basically an internal feedback loop where the brain rapidly error corrects its own sensory data until it settles on one single coherent interpretation.
So my experience of seeing a cat isn't just raw data. It's my brain saying, okay, let's run the model. Yep, turbo coding confirms 99% chance this is a cat.
It's the system's best guess. It's maximum a posteriori estimate. And this all connects back to that user interface idea we mentioned at the start.
The idea that I am not the computer, I'm the dashboard.
Precisely. Your laptop's hardware is incredibly complex. You don't interact with the magnetic charges on the hard drive. You click on a simple blue folder icon. The self is that icon.
So the self is a hack, a simplification.
It's a functional requirement for agency. The system needs to be able to say, I did that, so it can learn from the outcome. If I move my arm, I need to know it was me who moved it, not the wind, so I can take credit or blame.
So subjectivity isn't some magic extra thing, it's an engineering solution.
That's the argument. Without this user interface, you couldn't plan for the future or regret the past because there would be no you to star in those mental simulations.
Which brings up a weird paradox. We think, I have a thought, then my neurons fire. But we started by saying neurons firing caused the thought, so which is it?
This is the final section of the report, downward causation. The argument is that it's both. The software can, in fact, drive the hardware.
Oh.
That high-level integrated workspace, the synergistic core, once a pattern forms there, like the decision to focus on your work, that macro state constrains and drives the firing of the individual neurons below it.
So it's a two-way street. The neurons build the mind, and the mind directs the neurons.
It's a loop. And we see this breakdown in diseases like Alzheimer's. The report uses this chilling phrase, entropic attractor collapse.
What does that mean?
It means the brain is losing its complex structure. It can no longer support that high-level user interface. The hierarchy dissolves from the top down. The dashboard flickers and goes out, even if some of the hardware is still running.
And in a coma, it's different.
In a coma, the brain is often too orderly, too stable. It has low entropy. Recovery from a coma is literally the brain trying to find its way back to that critical state, back to the edge of chaos where complex thought is possible.
Wow. Okay, so to recap, we've gone from the tiny war at the synapse all the way up through ignition and criticality to this emergent user interface of the self.
From meat to meaning.
If you had to boil it down to one key takeaway for everyone listening, what would it be?
For me, it's that subjectivity isn't a thing that you have. It's a dynamical achievement. It's something your brain is actively doing every single millisecond. It's a balancing act on a tightrope, fueled by energy and maintained by sleep.
It definitely makes you appreciate a good nap.
You have to.
Yeah.
Without the downtime, the interface crashes.
Before we wrap up, I want to leave everyone with a final thought from all this. If consciousness really is just an engineering solution for the problem of agency,
Then what happens when our AI needs to solve that same problem?
Exactly. Right now, our AI is basically a level 2 zombie, a very smart prediction machine. But will a truly autonomous AI need a user interface to manage its own complex actions, to take credit for its computations?
And if it builds one, is that consciousness? It suggests you might not have to program a soul. It might just emerge because it's the most efficient way to run the machine.
And there's one last puzzle from the source that's still bugging me. They call it the Bayesian blur.
Ah, the final mystery.
What is that?
Well, your brain deals in probabilities. It calculates there's a 70% chance that's a cat, 30% chance it's a bag. The math is fuzzy, but you don't see a 70% cat. You see a sharp, definite
I
cat.
see 100% cat every time.
Exactly. So how does the brain turn a world of fuzzy, probabilistic math into the crisp, discrete, singular experience of now? That final step, from probability to actuality, that remains one of the deepest mysteries of all.
The mystery continues. Thanks for diving deep with us today.
My pleasure.
And to you listening, keep your synapses scaling and your workspace igniting. We'll see you on the next deep dive.